So I thought it might help a little bit to think about well-posedness in the context of the definition of a function, just to make it a little more clear. Hope this is a bit more abstract, but maybe also more clear. I'm not sure. You be the judge. It's just another way to think about it. So let's fix a partial differential operator. Fix a linear partial differential operator L. So we're just considering one problem, but allow the boundary data to vary. So let P be the set of possible boundary conditions and initial conditions, whatever your data is, for this particular problem. So these are the functions we typically denote by phi and psi, etc. And then let S be the set of possible solutions that you might get from this, right? And we'll define Q to be the solution operator. So it takes a problem to its solution. Now, maybe you're not used to thinking of functions like this, but you can define a function from any set to any other set as long as you properly define it as a function, right? And so this is how we're thinking about the process of solving a differential equation. And so we want this solution operator to be a function that takes a problem, phi, some boundary value or something, to its solution u. So Q of phi is going to be equal to u. Okay, so now for Q to be a well-defined function, so we're straight back in your set theory class, but don't worry, if you haven't taken 248, it won't matter today. Then, for something to be a well-defined function, first off, for every problem P, so any problem little p, there must be a solution. Okay, and so when you're defining a function on a given domain, in our case the domain is P, then every point in the domain has to get assigned to something, or else the function is not defined there. Okay, so this is our existence criterion for well-posedness. Also, it needs to be the case that for something to be a function, it has to satisfy the vertical line test, meaning that it can only assign a given problem to one specific value. So if Q of P is equal to S, and Q of P is also equal to T, so if a given problem gets mapped to the solution S and the solution T, then S has to equal T, because it can only get mapped to one thing. And so this is our well-posedness criterion of uniqueness. Now, for Q to be continuous, we need it to be the case that if we have two problems and they are close to each other, then it should follow that the resulting solutions are also similarly close. Or more precisely, the definition of continuity is all about limits. So we want it to be the case that if our problem varies continuously towards some other problem, then it should be the case that the corresponding solution converges to that particular solution. Okay, and so this is the kind of thing that we would typically write by saying the limit as P goes to P naught of Q of P is Q of our fixed problem P naught, right? And so if you are going to show continuity, so if you want to verify or validate continuity, you can think of trying to prove this statement, but it turns out that this is equivalent to and much harder to deal with than the simpler form, which is you look at the difference. So this is just a basic rule in analysis that typically it's easier to show that the limit of something goes to 0 than the limit goes to some non-zero thing. And the reason for that is because when you're going to 0, you also have that the absolute value goes to 0. And absolute values are handy to work with because you can get estimates, use squeeze theorems, sort of squash things here and there, get control of them one way or another. Okay, so now even better, if the PDE that we fixed back in the very beginning is linear and homogeneous, then Q is actually a linear function. And I'm going to call it an operator because it's a function that takes functions to functions, and such things are typically called operators. So Q is a linear operator, and that means that we know something about this expression right here that will simplify things. So this is further equivalent to saying that the limit as p goes to p naught of Q of p minus p naught is equal to 0. And so that's by the linearity of Q. And that means that in order to check whether or not Q is continuous, it's enough to check that it's continuous at 0, because anything else is just going to be, like checking continuity anywhere else can be shifted by linear change of coordinates to look at what's going on at the origin. So that simplifies things greatly. So you only have to worry about sequences converging to 0, not sequences converging to some random thing. And then you can use absolute values all over the place, which is super handy. And so it helps to sort of reformulate the way you think about this stability problem. So suppose we consider solution U for the initial condition phi. And then we also consider a perturbation. So a perturbation means we add something very small to it and see how things change. So let's consider a solution W for an initial condition psi epsilon rather, where this psi epsilon is so named because it is bounded by epsilon. Okay, so in other words, the idea then is that U plus W, at least on the boundary, so for t equals 0, yeah. The difference between these guys is very close. Wait, did I say what I wanted to say? No, hold on. What did I want to say? I wanted to say that U plus W is very close to phi. Yes. Okay. And then we'll see that it will follow to be the same way elsewhere. So we say that U plus W is the solution to the perturbed problem. With the initial condition phi plus something tiny. So we've just perturbed the initial condition phi here by some small amount. Wow, that pen is huge. Sorry about that. And then the question to be answered is, if W goes to 0, so as epsilon goes to 0, does this imply that U plus W goes to U? And again, that says epsilon goes to 0. And this is a different way to think about reformulating continuity just in terms of what's happening at 0.